Now let's look at one of the simplest machine learning algorithms called nearest neighbor classifier. Nearest neighbor classifier is probably really the simplest because it doesn't have any training procedure. It's basically at testing time, if you give me a new test example, I will assign the label according to the majority vote of the closest neighbors to that test example in the training set. For example, if you give me this test example, and the closest training example is this one, it should be labeled, so the test example should be labeled red for k equals 1. So 1 nearest neighbor, that is the nearest neighbor. But we often use k larger than 1. For example, if k equals 3, then these 3 data points in the training data are the 3 closest data points. And by majority vote, this test example should also be labeled red. But if k increases to 5, then we have 3 blue examples and 2 red examples are the closest to it. Then by majority vote, the test example should be labeled blue. Okay, so this is extremely simple. There's no training procedure at all. Every single other machine learning algorithm has a training procedure, and often training procedure takes much longer than testing time. Now we know that 1 nearest neighbor is extremely overfitting because let's say here's the data set and these are the boundaries, and we can see the boundaries are extremely nonlinear, extremely zigzag, right? Not smooth at all. So it's kind of overfitting. Because what if we have an outlier, right? Like say here, this is an outlier. An outlier would have kind of an island to itself, right? So that's bad. It's overfitting to the kind of noise in the training data. So we often use 5 nearest neighbor, or whatever, 10 nearest neighbor with a slightly larger k, which is better because the boundaries are a lot smoother, and an outlier like this will not be apparent at all. So this is an outlier in the blue ocean, so it will be neglected. So kind of the noise, some of the noise will be automatically silenced by increasing the k. Yeah, as we said, as k increases, the boundary becomes smoother and smoother, but you know, as we always say, as simple as possible, but not simpler. Think about what if k increases to infinity, right? What if k increases to infinity? Then you're just doing majority vote over all the training sets, right? If in the training set, the blue label is, the blue class is the majority, then every single test example will be labeled blue, regardless of where it is, regardless of what's the nearest neighbor, right? So that's the extreme case of underfitting. And the extreme case of overfitting is when k equals 1. So here's a quick quiz question, which is actually the last question in quiz 1. So to test your understanding of the first part of the first week of this course, think about leave one out cross-validation error for the following data set. That is 10 training examples, 4 positive ones, and 6 negative ones, using 2 different learning algorithms, 1 nearest neighbor and 3 nearest neighbor. What is the leave one out error for 1 nearest neighbor? And what is the leave one out error for 3 nearest neighbor? You can pause the video for a second and you can think about it. And the answer is 0.5 for 1 nearest neighbor and 0.1 for 3 nearest neighbor. Why? Because in 1 nearest neighbor, okay, each of these 5 points will be labeled incorrectly if it's used as the depth set or held out. For example, if you held out this guy, that is, you train out everything else and use that guy as a test example, and what label would it be? What's the closest training example? Well, this negative guy. So this positive example will be labeled as negative if it is used as held out. And same for here, same for here, same for here, same for here. So all these 5 guys will be labeled wrong if they were treated as a held out set, that is, to simulate the test data. And these guys will be labeled correctly. So it's half. Now 3 nearest neighbor, then these are also correct. What about this guy? What are the 3 closest data points in the training set? Well, this one, and this one, right? By majority vote, this guy should be labeled positive, which is correct, right? Same as for here, same for here, same for here. The only wrong case is in the middle, because the closest examples are, 3 out of these 4, because there's tiebreak. It doesn't matter. You can say, well, this one, that one, and by majority vote, this point is labeled positive, which is wrong. That's the only case that is wrong. So that's why it's 0.1.